Kinetic interpretation of temperature. Kinetic interpretation of temperature. We have to mention the kinetic interpretation of temperature. The average kinetic energy of translation. The average kinetic energy of translation of one molecule of an ideal gas. Average kinetic energy of translation. The average kinetic energy of translation of 1 mole of an ideal gas. Of 1 mole of an ideal gas at the absolute temperature T. At the absolute temperature capital T is Ek equal 1 by 2 m Vrms square. Ek equal 1 by 2 m Vrms square. This is equation 1 where m is the molar mass. M is the molar mass of the ideal gas. M is the molar mass of the ideal gas, and Vrms is the RMS speed of the gas molecules. Vrms is the RMS speed of the gas molecules. According to the assumption of kinetic theory of gases, according to kinetic theory of gases, pressure exerted by the ideal gas is P equal to 1 by 3 1/3 capital M by capital V Vrms square, where capital V is the volume of the gas, V is the volume of 1 mole of the gas, and capital M is the molar mass of the gas, or PV equal 1 by 3 m Vrms square, or m Vrms square is equal to 3 PV. M Vrms square is equal to 3 PV, or m Vrms square equal 3 RT. M Vrms square is equal to 3 RT. Using ideal gas equation, PV equal to RT for 1 mole of ideal gas, That's why m Vrms square can be written as 3 RT. M Vrms square is equal to 3 RT, which is equation 2. Using equation 2 in equation 1. We get Ek, which is average kinetic energy of translation of one molecule of the ideal gas. Ek is equal to 1 by 2 m Vrms square, or Ek is equal 3 by 2 RT. Putting the expression of m Vrms square, we get Ek as equal to 3 by 2 capital RT, where capital R is the universal gas constant and T is the absolute temperature. Here putting the expression of m Vrms square at this place, that means putting the expression of m Vrms square from equation 2, we get Ek as equal 3 by 2 RT. Ek is equal to 3 by 2 RT, which is the average kinetic energy of translation. This kinetic energy should be linear kinetic energy. That's why it is called kinetic energy of translation, not rotational kinetic energy. Ek is equal to 3 by 2 RT, which is the average kinetic energy of translation of 1 mole of ideal gas. 1 mole of ideal gas at the absolute temperature capital T, where capital R is the universal gas constant. Ek is equal to 3 by 2 RT. Therefore, the average kinetic energy of translation average kinetic energy of translation of one molecule of the ideal gas, average kinetic energy of translation of one molecule of the ideal gas at the absolute temperature, capital T, at the absolute temperature capital T, is given by Ek prime equal Ek divided by Na, Ek divided by Na, where Na is the Avogadro's number. Na is the Avogadro's number. Na is the Avogadro's number, that is the number of gas molecules, that is the number of molecules in 1 mole of the number of molecules of the gas in 1 mole of the gas, the number of molecules in 1 mole of the gas, or comma Ek prime equal 3 by 2 RT divided by Na. 3 by 2 RT divided by Na, where Na is equal to 6.023 into 10 to the power 23, 6.023 into 10 to the power 23 mole inverse, or comma Ek prime is equal to 3 by 2 under bracket R by Na, bracket closed, into capital T. Ek prime equal 3 by 2 R by Na into capital T, or comma Ek prime is equal to 3 by 2 Kt. Ek prime is equal to 3 by 2 Kt. Ek prime is equal to 3 by 2 Kt, where K is the Boltzmann constant, though it is pronounced as K, but it is written as Kb. K subscript B, Kb is the Boltzmann constant, and K is equal to R by Na, ratio of universal gas constant and Avogadro's number, which is equal to 1.38 into 10 to the power minus 23 joule per Kelvin. 1.38 into 10 to the power minus 23 joule per Kelvin, and Ek prime is equal to 3 by 2 Kt. This is the average kinetic energy of translation. This is the average kinetic energy of translation of one molecule of the ideal gas at the absolute temperature capital T. Ek prime is equal to 3 by 2 Kt, that is the average kinetic energy of translation of one molecule of the ideal gas at the absolute temperature capital T, at the absolute temperature capital T. Ek prime is equal to 3 by 2 Kt, that is the average kinetic energy of translation of one molecule of the ideal gas or per molecule of the ideal gas at the absolute temperature capital T. Therefore, Ek prime is directly proportional to capital T. Ek prime is directly proportional to capital T. That means average kinetic energy of translation per molecule is directly proportional to the absolute temperature of the ideal gas. Hence, the average kinetic energy of translation, per molecule of the ideal gas, that is the average kinetic energy of translation of one molecule of the ideal gas, is directly proportional to the absolute temperature capital T, is directly proportional to the absolute temperature capital T of the gas. Average kinetic energy of translation per molecule of the ideal gas is directly proportional to the absolute temperature of the gas. This is the kinetic interpretation of temperature. Kinetic interpretation of temperature. That is, kinetic interpretation of temperature will be what? The average kinetic energy of translation per molecule of an ideal gas is directly proportional to the absolute temperature of the gas. The average kinetic energy of translation per molecule of the gas is directly proportional to the absolute temperature of the gas. That is the kinetic interpretation of temperature. Also, at the absolute temperature T equals 0 Kelvin, Ek prime is also 0, as Ek prime equal to 3 by 2 kT. Therefore, half m Vrms square will be equal 0. Half m Vrms square will be equal 0. Therefore, Vrms is equal 0. Vrms is equal 0. Vrms is equal 0, that is the RMS velocity of the gas molecules. Therefore, the root mean square velocity of the gas molecules, reduces to 0 or decreases to 0 at absolute 0 temperature. That is the molecular motion ceases. The molecular motion ceases at the absolute 0 temperature, or at the 0 Kelvin temperature. Vrms is equal to 0. That means molecular motion ceases at the absolute 0 temperature. Another kinetic interpretation of temperature will be what? Root mean square velocity of gas molecules reduces to 0 at absolute 0 temperature. That is, molecular motion ceases at the absolute 0 temperature. We get two interpretation of temperature. One is average kinetic energy of translation per molecule of the gas is directly proportional to the absolute temperature of the gas. And another kinetic interpretation is root mean square velocity of gas molecules reduces to 0 at absolute 0 temperature. That is, the molecular motion ceases at absolute 0 temperature.